Hello, physics students. Mr. Williams here, and today we are going to be talking about thermal energy and work, and specifically how changing an object's thermal energy can change the system itself and cause expansion. So, work energy theorem, bring it back. We know that work can be done to increase an object energy, or we can use energy to do work. So, work can be done to increase the energy of an object. Since thermal energy is a type of energy, we should expect that we can do work to increase a thermal energy. We've been looking at cases where we do work to increase mechanical energy, the energy of motion. Like you apply a force, it moves some displacement, and it's going to speed up as a result, or you're going to increase its height. But often in cases of mechanical energy, we ignore friction. But friction has its own different kinds of energy transfer. Friction does work, but it does not transmit that work is not transmitted into a kind of mechanical energy. It's turned into a thermal energy. So an example of doing work and creating heat is just rubbing your hands together, as you can see Patrick is doing right now in this GIF. Doing this will increase the heat energy of your hands, and you can feel it right there. So work can be done to increase the energy of an object or vice versa. So this kind of leads us to thermal expansion of the temperature changing and work kind of being done on the particles themselves. So think back to our kinetic theory of matter, that all objects are made up of particles. Well, as particles heat up, they vibrate faster, increasing the space between them, as we can see in this first diagram. Well, that microscopic increase between atoms, it's going to be multiplied 1 billion times over, and it actually causes objects to grow and shrink by a measurable amount when their temperature changes. If you have taken chemistry, then you probably have learned of the ideal gas law, which was the PV equals nRT, and it tells us that pressure, P, is proportional to temperature, or not pressure, I wanted to talk about the volume is proportional to temperature. As temperature increases, volume also increases. That this is how matter behaves when we're looking at an ideal gas, or like a liquid can also work here, or even a solid. As temperature goes up, volume is also going to go up, and we see that in the diagram below. So, chemistry aside, this has physical implications that things actually expand when then their temperature changes. We can look at a linear expansion of this. And it makes sense that not all substances are going to expand at the same rate. Solids are going to expand less than liquids, and liquids expand less than gases. So, and think even between solids, metals are going to expand quite a bit when heated, while glass is barely going to expand at a temperature change. So we have this quantity that we know as the coefficient of expansion. It's this A subscript L divided by degrees C. Describes how an object length will change for a given temperature change. And here are some common coefficients of expansion. Notice they're pretty small values. This leads you to believe that a small temperature change, like if I just go up by 1 degree, are we going to change that much? No, that's a very small number if we just have 1 degree temperature change. But with larger temperature changes, we can get larger length changes. We can put all that into an equation, which we see here. This equation tells you what the change in a length will be given 3 different things: the coefficient of expansion, AL, the initial length, L, and the temperature change, degrees, T. So depending on those 3 factors, we can calculate exactly how much an object will expand. Can do 2 examples of this. In the first, here we go. In the first, we have a gold bar initially 2 meters long. That is my L. Its temperature is 20 degrees. How much does the bar expand while its temperature increases to 140? Well, I know L is 2. I know delta T is what I really want to know, is on 120. I subtract there. And then I just need to know what my AL is. I don't know why I did AL. Come on, give me my thing. AL, and I know that it's a gold bar, so I can take a look back and see in my table for gold that my coefficient is 14 times 10 to the negative 6, so that's the value that I want to do there, 14 times 10 to the negative 6. I can throw all of that together and get delta L. My change in length is going to be 2 times 120 times 14 times 10 to the negative 6. And I'll let you figure that one out there. You can do the same thing for the second one. We see the initial length is L. It's 100. Its temperature is increased by 50, so we already know the delta T, and its length increases by this much, so we're given delta L. We want to know, what is this object most likely made of? Well, we can use the same equation. Delta L equals L, I'll just do it like that, L times AL times delta T. And notice we know all of these values. We know delta L is 0.055. We know delta T is 50. We know L is 100. So we can rearrange this equation and solve for AL. Once we get what AL is, we're asked, what is the object most likely made of? Well, we can just compare this to the table. So for this problem, you're going to solve for AL, and then look at this table. What do you think AL is based on, once you have AL, what number does it match with? Lead, aluminum, brass, gold, steel, or Pyrex? All right, and then that's how you'll solve that problem. Now for the lastly, we can also expand in volume. It doesn't have to just be length. So we can expand in one dimension, which is length, but it's the same as really expanding in 3 dimensions. Objects are generally made up of 3 different dimensions. So if I have a box and it expands both in the length and in the width and the height, it's going to increase not just one of those, but all 3, and then so the volume changes. And you can see the expression for volume expansion is almost exactly like linear expansion, just the change in volume. A V, now the coefficient of volume expansion, times the initial volume times the change in temperature. So it's pretty easy to do volume expansion if we can do linear expansion. So I trust you can apply that. All right, that's everything for